Happy Wednesday, Baylor College of Medicine and friends of Baylor College of Medicine. The good news is Christmas is coming up, so it should be a really exciting time, of course. Just so you know, I have a holiday tradition. Every Christmas, I used to go to New York City and spend Christmas Eve with my sister, my lovely sister Janet, who I hope you've all gotten to know. And then with my in-laws, and every year walk down Madison Avenue on Christmas Eve because it's so great. Well, of course, because of COVID, none of that can happen. So that's not happening. It's going to be very just nuclear family Christmas and holiday season. So I know we're all suffering for that, but it's just something we got to do. Great news: the vaccine's being distributed. People are actually getting injected. It's all going to be very positive. Hopefully, in the next several months, we will begin to see some relaxation of things. Maybe. But the good news is there's been a lot of focus on the mRNA vaccines that we have from Pfizer and Moderna, and appropriately so. They're the first ones in. But I think one of the things everyone's been concerned about, and you've heard a lot on the news about supply chain, is there going to be enough? Why does it take so long? And that is a big issue. And when you think about how are we going to return to pre-COVID state, it's not just we feel good going out to dinner in a restaurant. You know, people want to travel places. You know, I've got folks who want to go to Brazil. I got people who want to go to Mexico, want to fly to Europe, take some time off. Until the rest of the world begins to come along and reach the same kind of herd immunity, things are going to be better for us in the U.S. in that we will begin to return more towards our normal social life. But we still, that's going to make it very hard to travel internationally and do all the things we've done pre-COVID. So the reason why this is important is there are other vaccines being developed that are much easier to produce, cheaper, and easier to distribute. So while we in the U.S. are very focused on Moderna and Pfizer, there are other ones coming down the line. So I thought it would be useful for everyone just to think about these vaccines and what is available and what's going on in the rest of the vaccine development world. So one really interesting thing, we now know that 2 doses are required for the mRNA vaccines to get complete immunity. The Moderna vaccine requires 2 doses, 4 weeks apart, 95% effective. It's interesting, in the Moderna trial, the trial was stopped when they got 196 cases. Well, all but 11 were in the placebo side. The 11 that were on the vaccine side, which is why it's only 95%, not 100%, but the 11 all had mild cases. So one of the claims is that not only does it prevent the disease, but at a minimum it prevents some severe disease. One of the things we don't know that'll take long-term follow-up is do you get infected at all? If you do get infected, can you transmit? Does this prevent transmission? So lots of questions to answer yet. There's also a German company, CureVac, that's in phase 2. And it's really interesting. So to get around the distribution issue, they are working with Elon Musk to create microfactories all over the world. So rather than try and get a central factory and distribute, they're going to try and make little factories everywhere to get around all the distribution issues. There's another company in China and Thailand also doing mRNA vaccines that are in preclinical trials. So other countries also working on a similar kind of platform for mRNA vaccines. I wanted to bring up one that's very, very cool. This is the self-amplifying RNAs. These are all in phase 1-2 trials. And what a self-amplifying vaccine, and it's really kind of fascinating. What they use is an alpha virus. Alpha viruses are broad in many, many species, rodents, fish. It provides it causes some of the equine encephalitis, but the cool thing about these alpha viruses is they're single RNA strand, a positive coding strand, and you can combine the replicon, the gene that actually causes the replication, the replicase. you can combine that with your protein that you want to make, the thing that you want to generate the antigen to be your vaccine candidate. So you put that on the backbone of a positive RNA strand, and what happens is the replicase replicates the positive strand, makes a negative strand, and then uses that template to make a positive strand again. The replicase also makes all the protein that you want to generate for the antigen. And so what this does is, without having a live attenuated virus, a real virus that's replicating in you, it just has an RNA strand that keeps duplicating itself. And what that does is it acts like a long-term attenuated virus. So there's antigen produced constantly, and that will likely lead to better long-term immunity. We assume there won't be complications. That's why it's in early development, but it's a really cool idea. And if you think about why poliovirus is so incredibly effective, it's because it's a live attenuated virus that lives in you and constantly is creating polio antigens. So those are under development even as we speak. Then there's a bunch of DNA-based viruses, or DNA-based vaccines, and these are a lot more stable, but are a little harder to actually get into cells. And so there's several companies in Japan and India and in the United States. They're working on DNA-based vaccines. So instead of having the RNA, it's the DNA. The concern with DNA is that it might get into the nucleus and have a recombination event. So the concern is they're less safe. But there's some cool ideas of how to get DNA into cells, and mostly they involve skin applications, either under the skin, like an insulin shot, subcutaneously as it's called, or delivered with little electric pulses. You just place it on and use electric pulses, much like you're getting a tattoo. You'd get a vaccine. And there's one that's even working on a skin patch that you would have a DNA on the skin patch that you would just put on, and that would eventually be absorbed and be your vaccination. Now, the other thing that is being used a lot are these virus vectors. Adenovirus vector is the one that is most commonly used, and that's because the adenovirus vectors have been used for gene therapy for decades. So we have a lot of experience with adenoviruses, and those are the ones that are being used for the AstraZeneca and the Johnson & Johnson ones. Now, there are a bunch of companies using adenovirus 5, which in my view is probably not the greatest adenovirus vector, because we get that. People get that. Kids get adenovirus. It causes an upper respiratory infection. And if you've already had adenovirus 5 infection, if you put that, and it's an empty virus, it's not replicating, but you put the antigens that make the virus to surround the RNA or the gene, actually, in this case, the gene that you're going to express the protein, there's a good chance that you're going to react to the adenovirus 5 vector. And so you'll generate a lot of antibodies to the adenovirus rather than the proteins that are being made for the coronavirus. So that's one of the concerns. So the way to get around that is what Johnson & Johnson did, used adenovirus 26. It's one of the serotypes that's around there, many serotypes. But adenovirus 26 is one of the rarer ones. People don't get it that much, and so it's less likely that you'd have a giant immune reaction to the adenovirus 26. So that's the Johnson & Johnson one. AstraZeneca is using one that's in chimpanzees. So presumably, unless you've been hanging around a bunch of chimpanzees, you should be okay. So those are the viral vector ones that are coming online fairly soon. So we should have results from Johnson & Johnson by the end of December, by the end of this month, early January 1. These are a little bit easier to store, so it'd be easier to distribute. So far, at least the Johnson & Johnson one was 1 dose. They started another phase trial to do 2 doses, which suggests to me that it's not as effective as the Moderna or the Pfizer vaccine. Otherwise, it wouldn't do a second trial. The preliminary studies showed that it was about 70% effective, and so I think they're going to try a 2-dose regimen to see if they can't get it up to 90 or 95% like the other vaccines. So we'll see, but a single dose obviously would be a lot easier to do, and it's easier to store, would be easier to distribute to the rest of the world. There's a bunch of other viral vectors that are being considered. One is a weakened influenza virus. There's been some studies in actual influenza viruses that use one that's cold adapted. So what that means is it's grown in cold conditions, so it can only grow in cells that are cold. So if it's in the body, which is hot, it can't grow. So where this cold adapted influenza virus lives is at the tip of your nose. It's the only place it can survive. Well, you can use that influenza virus to also make coronavirus vaccine, coronavirus proteins. And so there's one, Merck is doing an exploration of a weakened influenza virus that also will make corona spike proteins. And there's a bunch of other companies in Hong Kong and China that are also doing the same thing. There's another interesting vaccine that's been used before. It's modified vaccinia. Vaccinia is the kind of viruses that cause smallpox. Well, what happened over the generations of making these modified vaccinia viruses is they've adapted them in cell culture so they will only grow in avian tissue, won't grow in human tissue. And so it can infect you. It only infects chicken cells. And so that modified vaccinia was being used to create a vaccine for MERS, the Middle East Respiratory Syndrome, very similar to another coronavirus. It's also being used in H5N1, Ebola. So I think that those will be coming along also as potential viral candidates that'll be effective, and also again very easy to store. And just so you know, there's a bunch of other ones. One of the interesting ones that's being looked at is vesicular stomatitis viruses. It causes cold sores. That can be used as a way to give oral vaccines. And there's a virus called adeno-associated virus, which is a single-stranded DNA virus. The advantage of AAV versus other DNA viruses is at least that virus integrates in a very specific place in the genome, so you know it doesn't mess things up. That one might be one that could be used and adapted for long-term strategies. So those are all the viral vector ones. Then there's ones that are just the old-fashioned way. Make the spike protein and give it. And that is kind of the old-fashioned, easy, well-established way. And Novavax is starting their vaccine trial. This one is really cool because it takes a bunch of spike proteins and puts them on nanoparticles and then injects those into people. And so your body will respond just as though the mRNA ones I've told you about make the protein and then it's released and immune responses respond to that released protein. Well, it's the same thing as just giving the protein. And you get an antibody response to that. Not as strong as getting the T-cell immunity response, but you certainly get an antibody response. So that's starting soon. There's also a bunch of different ways to make the protein. You know, you've got to generate the protein. It can be done in bacteria, it can be done in mammalian cells. One of the newer ways to do it is grown in tobacco plants. So, you know, tobacco is not good for you to smoke, but it may be really good for generating vaccines. And actually, people may not know this, but Admiral Giroir, who's been the vaccine czar under Trump, when he was the chancellor at Texas A&M, they built a giant tobacco mosaic plant facility for the generation of proteins for just this kind of purpose. So I haven't spoken with Texas A&M yet, but we probably ought to got a Chancellor Sharp on the phone and see if we can do something there. And then, of course, there's the usual proteins being made in insects or mammalian cells. The reason sometimes it's good to make it in those kinds of cells is when a protein is made, there's all kinds of modifications that happen to the protein to make it look like a real protein, not a fake one. And so those kinds of substitutions happen in mammalian cells, also in insect cells. And we're very excited, of course, about the one that Texas Children's and Baylor College of Medicine are collaborating on, Peter Hotez's vaccine. That should start, that's in phase 2 or 3 in India. That's BioE. We're really excited about that one because I think if that one is efficacious and it's so cheap and stable, right now the plan is to make 1 billion doses in India, and hopefully we'll start getting some of the results from those vaccines. So that's sort of a summary of all the different vaccines. There are literally almost 100 vaccines in development. We're getting more and more through to phase 3. We've had 2 now that have been basically approved for emergency use. I assume they will be shortly approved by the FDA and all the appropriate committees so that It'll just be like any other development of any other vaccine. And I want to stress to everyone, they go like, well, why did it take 20 years to do a vaccine, and now we're doing it in a year, 2 years? There's two really important things. First, science. The science is really been fantastic, and it's been developed over decades. So as I mentioned a couple of weeks ago, the way these mRNA vaccines, they've been in development for 30 years. And just having them ready and already in phase 2, 3 for other viruses, once you have the mRNA platform and the liposome, the lipid bilayer that goes around them, you can put in any protein anytime. So that should be transformative in terms of speed to development. But the second most important thing that people don't think about is that the U.S. government basically took away all the risk from the companies by basically prepaying for development. Literally billions of dollars were given to the companies to invest in really very iffy technologies, but to get them going, and also prepaid for the vaccines if they were successful. So if you're running a business, you have to think like, what's the financial risk to me? And that's a major barrier to speed. You want to wait to make sure every step along the way is positive, because you don't want to suddenly invest a huge amount of money and find out you have a failed vaccine. But the government, and this give the Trump administration credit, the government took away that risk. So the financial risk was removed. But it was the science that made the vaccines and the long-term development of the science that allowed it to come to fruition so quickly. I hope this will be transformative. If we start thinking about the future of vaccines and development in our country, it shouldn't take 20 years. And hopefully we will be able to generate vaccines quickly, within a year, and I hope the federal government will continue to support the development of these vaccines and take some of the risk away from these small companies who otherwise would not be able to financially really take the risk to create the vaccine. So lots of good things. I think it's a victory for the partnership between government and science and the for-profit world and companies. So a lot of positive things that came out of this otherwise disaster for us and for our public health system. So how are we doing in Texas? We continue to rise. We still have capacity to take care of people. We're not as bad as other parts of the country, but it really still reflects the surge that happened in the fall. I think we have 2 or 3 months of real problems ahead of us just because of the number of people who've been infected. But start thinking about when, if we start getting to 60, 70% of the country vaccinated, we can do this. This is something we can do. It's really an operational issue. It is not a discovery. Discovery is much harder than operations. This is logistics and operations. And I think by June 1st, in our region, in Texas, I think in all the urban centers that have easier availability and ease of giving the vaccines, I think you'll start seeing herd immunity and us being able to almost take off our masks and behave normally by sort of the early to midsummer. I think the fall, I would pretty much count on football returning in the fall, where we can all get together and start behaving like the way we really want to. I think it's going to be longer before you can maybe fly to India or go to Colombia. It's going to take a little bit longer for the rest of the world, I think, to catch up. Europe will be fine, but I think that there are remote places in the world that are going to be slow to get vaccines and slow to be vaccinated. And the risk really is to their population. It's not so much to us, but if now the world starts traveling around again, all you need is one person, as we talked about in that Maine super spreader event. Go to a naive community, and all it takes is one person that's infected. And so I think they'll remain fairly serious travel restrictions until every community can get up to what is importantly herd immunity. So as we end the year and we start thinking about the Christmas holidays, I think it's a good time to reflect on all the good things. our community, Baylor community, has come together incredibly. Whether it's supporting our students, our staff that work here, our scientists, our educators, our physicians who tirelessly come to work and take care of sick patients. It's been a great community response for the Baylor College of Medicine. And Texas, I mean, you got to give Houston a lot of credit. The Texas Medical Center came together. All of the people who competed normally came together and collaborated to really to help us deal as a community with this global pandemic locally. And our leadership at the mayor's level and the county judge. That the county judge was criticized heavily for enforcing a mask order. Well, she was right. And of course, as we go into the holidays, I want everybody to think about all that everyone's done. The number of people who are truly suffering in this country. We, are doing better than others. We should be very grateful as we go into a holiday season for what we have, not for what we're missing. We really have more than so many other people. So lastly, because it's a smaller Christmas, we're avoiding the multi-family get-together. I say it's a sacrifice that I can't be with my in-laws, but no, actually. I hope they don't see this now. But Tony, I didn't mean to you and Sarah. Tony and Sarah, I didn't mean that. But I'm going to miss all of my in-laws. So we're going to have a much more focused party in the Klotman house. And the hardest thing for any father, of course, is picking out what holiday outfit their daughter is going to wear. And so I've been struggling. As you know, my wife is in North Carolina doing her dean thing at Duke. That doesn't help me picking out a dress for Lily. And so I need your help. This is me asking for your help. We have a little show at the end. I've picked out 2 outfits, but one's a little kind of cheap looking, but I'm going to let you all decide. Please vote. Send in to president@bcm that email whether you like the one outfit or the other, and that will be the outfit that Lily wears for the holiday party. So thank you. Have a wonderful Christmas. Thanks for everything you do for Baylor College of Medicine. Thank you for all the people following us. We really love the support that you give us by just tuning in, and I will see you next week.